Equations are the lifeblood of mathematics, science, and technology. Without them our world would not exist in its present form. The course of human history has been redirected time and time again, by equations. Equations have hidden powers. They reveal the innermost secrets of nature. As Steve Jobs said in his iconic speech at Stanford, we cannot connect the dots looking forwards, we can connect only looking backwards. Let's look back at our past, and the journey up till now. Let's look back at the top 10 equations that has changed the world. Number 10, Pythagoras theorem. A squared plus b squared equals to c squared. This equation reaches far beyond its domain of geometry and algebra than perhaps any other equation on this list. The simplicity is its power. This equation revolutionized our way of perceiving distances, linked geometry, and algebra in such a way that it gives birth to the coordinate system, or more specifically, how we measure distances in terms of coordinates. Our knowledge about its origin is very little and obscure. We are not sure Pythagoras even invented it. Babylonians, in 2nd millennium BC, 1000 years before Pythagoras, knew the relations between Pythagoras triplets. It is possible though that Pythagoras was the first one to prove it, which he did, around 530 BC. It attained its first recorded proof and its most polished form, in 250 BC when Euclid clearly wrote about it in his famous textbook, Elements. He wrote, in right-angled triangles, the square on the side subtending the right angle is equal to the sum of the squares on the sides containing the right angle, the translation being made possible by Sir Thomas Heath. We don't know how Pythagoras' theorem got its name, but whatever and whoever the reason is behind its existence, it sure paved the way for a whole new frontier of science to follow. Number 9, Logarithms. Log of xy equals log of x plus log of y. At first look, you might doubt its position in this countdown. However, look a bit deeper and you would see that nothing, absolutely nothing in modern-day science would work without it. Logarithm was developed with just one purpose in mind, to make multiplications easy. It does so by changing multiplication of two numbers into addition of two. You might think 2 multiplied by 3 is a lot easier to solve than e raised to the power ln2 plus ln3, and you are right. It is. However, it was not devised for doing 2 cross 3. It was devised for astronomical calculations, which is way more complex than 2 cross 3. Multiplications, at that level, in those days, were beyond tedious. Logarithm was invented by John Napier and he first published it in his book, Mirifici Logarithmorum Canonis Descriptio, Description of the Wonderful Canon of Logarithm, 1614. However, it was Henry Briggs that made logarithms the way they are today. He proposed the following corrections. Number 1, the base of log should be greater than 1. And number 2, the idea that log of 10 equals 1, thus drastically reducing the fatigue of calculating log 12.34567889, if you knew log 1.23456789. Logarithm is an indispensable tool in the toolbox of a mathematician and also calculus. Evolution pretty much had to come up with something like a logarithmic scale because the external world presents our sense with stimuli over a huge range of sizes. A noise can be very low or very loud. An ear made sensitive enough to hear the little sounds would be destroyed when hearing a loud sound.
Watch out for the shock, it's coming.
Conversely, an ear made to hear loud sound wouldn't be able to hear little sounds at all. That's the problem with being sensitive to absoluteness. Rather, being sensitive to proportions make excellent sense. Logarithm does exactly that. Example. Say you can hear a sound in a range of 1 to 10 units. If you perceive stimuli in absolute scale, you can hear sound, only up to 10 units, after which your ears will be permanently damaged. However, if you follow the logarithmic scale, which we do, instead of absoluteness, you will focus on ratio. Say you can perceive a minimum difference of 2x, then, you would be able to hear sounds of units, 1 to 1024. The only fault you will have is that when you hear two multiple sounds simultaneously and if they differ by a factor less than 2, they would sound the same. Also, you won't be able to hear the range, 0 to 1, and 1024 to infinity. But it's a small price to pay comparing to what you are getting. Number 8, differentiation. Change of dependent variable with respect to independent variable is equal to the ratio of the change in functional value for an increment, to that of the increment itself where, the increment tends to 0. What can be said? The entire mathematics and physics, even parts of chemistry and biology, depends on calculus, which would not have been possible without derivatives. Let's start with the most important question in calculus: who invented it? While both Gottfried Leibniz and Isaac Newton discovered calculus more or less independently, however, we are not sure who did it first. That is because none of them published their works as soon as they got the results. Newton's work dates back to 1671 while Leibniz's to 1675. To make things messy, the approach of Leibniz was more efficient and promising. Making things worse, the notation we use in calculus now, are borrowed from both of them by dx from Leibniz and f' of x from Newton. I think it boils down to this: just like Pythagoras' theorem, it doesn't matter much who invented it as much as who introduced it. It was Newton who introduced calculus into the world, who used it to study the laws of nature, and I think that is the reason Newton is often credited more than Leibniz. Also, it is justified. I think the world couldn't be less grateful to him for introducing calculus into physics. However, we cannot give all credits to Newton for his calculus, for, no matter how grandeur, it was flawed. A leading critic, an Anglo-Irish philosopher, George Berkeley, Bishop of Cloyne, felt Newton's discoveries as an attack on religion and attacked back by calling derivatives ghost of departed quantities, and questioned the very foundation of calculus, the non-zero number h, which we, after calculation, make equal to 0. How can we divide something with 0 in the first place? His question was spot on. The solution to this key question was limits, which came in 1816 by Bohemian mathematician Bernard Bolzano, but, like all tragic stories, it was never appreciated till 1870 when German mathematician Karl Weierstrass extended the formulae to complex functions. After the advent of limits, the very foundation of calculus was reformulated. Nowhere in the calculation do we ever divide by 0 because we never set h equals to 0. Moreover, nothing here actually flows like Newton originally described. What matters is the range of values that h can be assumed with, not how it moves through that range. So Berkeley's sarcastic characterization is actually spot on. The limit L is the ghost of departed quantity, my h and Newton's O. But, the manner of the quantity's departure, approaching 0, not reaching it, leads to a perfectly sensible and logically well-defined ghost. Finally, calculus had a sound logical foundation, and it was now all set to redefine the world. Number 7, Newton's law of gravity. F equals to gravitational constant multiplied by m1 into m2 divided by square of the distance between the bodies. Newton's influence on the revolution of science and the way we understood nature is never-ending. Newton was not the first of the age of reason. He was the last of the magicians, the last of the Babylonians and Sumerians, the last great mind which looked out on the visible and intellectual world with the same eyes as those who began to build our intellectual inheritance about 10,000 years ago. Isaac Newton, a posthumous child born with no father on Christmas Day, 1642, was the last wonder child to whom the Magi could do sincere and appropriate homage. 5th July, 1687, Newton's Philosophiae Naturalis Principia Mathematica, the system of worlds, re-evaluated our and above all, God's position in this universe. Newton's law of gravitation synthesized, in one simple mathematical formulae, millennia of astronomical observation and theories. It explained many puzzling features of planetary motion, and made it possible to predict the future movements of the solar system with great accuracy. Einstein's theory of general relativity eventually superseded the Newtonian theory of gravity as far as fundamental physics is concerned, but for almost all practical purpose the simpler Newtonian approach still reigns supreme. Today the world's space agencies like NASA and ESA still use Newton's laws of motion and gravitation to work out the most effective trajectories for spacecraft. We cannot talk about gravity without talking about the famous apple story, which was first mentioned in 1752, Memoirs of Sir Isaac Newton's Life, by William Stukeley. After a deep investigation, the truth, if it is even, is that no, Newton didn't realize gravity by the falling apple. However, gravity is not that important itself. Words about gravity was in the air for a long time, far before birth of Newton, but what apple probably did was that it made Newton realize the universality of gravitation. It is this very reason why Newton, more than anyone in history, is credited for gravity. It was he who proposed that not just sun but everything that has mass attracts everything else, and the force with which one body attracts another, is mutual. Out of all the innumerable things that Newton's law of gravity made possible, the latest and the most amazing one is called gravitational network tubes. It's an idea straight out of sci-fi. It has been observed that planets and moons of the solar system are tied together by a network of tubes, whose mathematical definition requires many more dimensions than just 4. They can be seen only through mathematical eyes because they are not made of matter. Their walls are energy levels. If we would visualize the ever-changing landscape of gravitational fields that control how the planets move, we would be able to see the tubes swirling along with the planets as they orbit around Sun. Without going into further details, the discovery of tubes took the efficiency with which we could space travel to a whole new level and redefined the method of plotting the best trajectory for interstellar missions. All of which would not have been possible without Newton and his epic law of gravity. There is a tie for the number 6 spot. It is held by I square equals to -1, square root of -1. And also by Euler's formula for polyhedral, Fe plus V equals TO2, where F is face, E is edge and V is vertices. It led to the foundation of complex analysis, which is now even more important than real analysis in areas like statistics, mathematics, and mathematical physics, especially quantum mechanics. The one who knows this must hate this equation at first sight, and one who doesn't know, must be thinking what's so special about it? Well, it all began in 1545, when gambling scholar Girolamo Cardano first encountered this while writing an algebra text. He couldn't make sense of it and declared it useless. Then come Raphael Bomelli and thought he could certainly do better. By 1572 he had noticed that, these numbers, despite being baffling and nonsense, they did lead to perfectly correct results when used blindly. It took almost 18th century for scientists to finally get an idea of what it is. By 19th century, scientists started feeling comfortable about it. However, by the time they were truly understood, they had already become indispensable in mathematics and science, and its definition hardly mattered. With the dawn of 20th century, the so-called imaginary numbers seemed no less real than their older cousins, the real numbers. It all started when there was a concept that squares are always positive and defined. It was Renaissance time, and the concept sprang from their logic that no matter what you do to a square, double it or vanish it whole, the least you can reach is zero, not negative, i.e. even square, doubling, is always greater than equal to zero. Leibniz on 1702 wrote, "The divine spirit found a sublime outlet in that wonder of analysis, that portent of the ideal world, that amphibian between being and non-being, which we call the imaginary root of negative unity." The first one to make sense of them was Wallace, 1758. His idea was then improved upon by Bessel, 1797, Argand, 1806, and Gauss, 1811. It came to gain wide acceptance when calculus was expanded to complex realms. Euler also contributed by merging the realm of complex and trigonometry by giving his formula e raised to the power iz equals to cos of z plus I sin of z. For z equals to pi, e raised to the power I pi equals minus 1 plus 0. Or, e raised to I pi plus 1 equals 0. This equation has been voted time and time again as the most beautiful equation in mathematics. It unifies calculus ESE, trigonometries pi, complexes I and algebras 1 to give the ultimate number 0. It is based so deep into the current model of mathematical analysis and modern physics that you cannot do anything without them. You either learn it or close your eyes. To see nature, as God mean it to be, you need an eye. While I changed one pillar of mathematics, Euler changed the other. Euler was the man who single-handedly changed the very face of mathematics. He published more papers than any other scientist in the history and has also contributed most number of equations to mathematics, thus making him the rightful owner of the title the greatest mathematician of all time. Why is this formula important? Well, before it, the three pillars of pure mathematics were algebra, analysis, and geometry. After this formula, it became algebra, analysis, and topology. This founded a whole new branch of mathematics where shapes never matter, only the points do, for the sheet here is elastic. This revolutionized the way we approach any problem related to geometry. When asked, Euler said this has nothing to do with maths, it's just observation. Don't know how anyone never noticed it? I do not think this can be explained in simple terms here, for the time and knowledge required to know more about it is way beyond many of us. For now, let's just end by saying that when a formula results in equation of a whole new pillar of mathematics, you can guess how important it is. Number 5. Wave equation. Del square of u, by, del t square, equals to, v square, into, del square of u, by, del x square. Where u equals to, x, t. Very basically, say a wave is propagating. Delta x equals tov of delta t. For a parameter u, x, t. Del u by del x equals to del u by v del t. Again. Del square u by del x square equals to del square u by v square del t square. For limit, del tends to 0. Del square u by del t square equals to v square del square u by del x square. This helps us visualize how a wave propagates. The greatest use of this is in the study of earthquakes and tsunamis. Thus, you can understand how important it is. This gave birth to acoustics, the interdisciplinary science that deals with the study of all mechanical waves in gases, liquids, and solids, including topics such as vibration, sound, ultrasound and infrasound, or the other way around. This equation exists only because scientists wondered, why does the strings of violin create sound? It took birth from the fundamental elements of music, that is, harmonics. For same tension to string, different length produced different sounds. Some were unpleasant and some touched the hearts. It is this curiosity to reveal the secret of music that leads scientists to discover a formula, which now predicts the height of a tsunami wave. It all started with Pythagoreans, the cult founded by Pythagoras. It was reported by around 150 AD. However, it was D'Alembert who proved the equation in 1746, by applying Bernoulli's approach to Newton's second law of motion. From then, it spread across the world of science like a forest fire. It is extensively used to drill out all the quadrillion-dollar industry. Nowadays, explosions are made at the surface, and using the principle of returning echoes of the seismic waves, they map out the underlying geology, and hence find where oil is. Number 4. Fourier transformation. F of epsilon equals to integration minus infinity to plus infinity f of x, e raised to the power minus 2 pi x epsilon, dx, where epsilon is frequency. What is this? Well, what it does is that it transforms any function into a function of multiple sinusoidal waves which, when drawn, superimposes to give back the original function. Why is it important? Well, without it genetical development would have stopped at the foot of the ever-popular DNA molecule. It is this series that led to the analytical study of DNA and thus pushed the mankind to a whole new level of intelligent species. For a more daily example, Fourier series is used in image processing. The thousands of selfies you take would not have been possible without it. The very format of JPEG would not have been possible without this. How? Well, first let's see how it was discovered. It all happened when Fourier in 1807, submitted an article on heat flow to the French Academy of Sciences based on a new differential equation. Although that prestigious body declined to publish the work, it encouraged Fourier to develop his idea further and try again. At that time the Academy offered an annual prize for research on whatever topic they felt was sufficiently interesting, and they made heat the topic of the year for the 1812 prize. Fourier duly submitted his revised and extended article, and won. His heat equation was del U by del T, equals to alpha into, del square U by del X square, where, U is the temperature function and alpha is constant of thermal diffusivity. It is almost similar to the wave equation except it has del square by del T square. The difference is huge. It means that in wave, energy is conserved, but in heat flow, it was not so. However, while solving this equation for trigonometric profile, from there sprang out this brilliant conclusion that any function continuous or discontinuous can be represented as superposition of sinusoidal curves, provided we have enough of them, that is, an infinite series of sine curves. After all, the solution was insufficiently rigorous and every scientist discarded his prize-winning formulae. We now know that although Fourier was right in spirit, his critics had a good reason for worrying about rigor. The problem was, when does the Fourier series converge to the function it allegedly represented, that is, if you take more and more terms, does the approximation to the function get even better? Even Fourier knew the answer was not always. Resolving it was tricky. It required a new theory of integration, by Henri Lebesgue. A reformulation of the foundation of mathematics in terms of set theory was made by George Cantor, and major insights from towering figures like Riemann. Fast forward the time and now, it is being used everywhere. Stripping out unnecessary frequencies from the source signal to reduce your telephone cost to making buildings that can efficiently absorb earthquakes. Its greatest impact is perhaps in the digital revolution. You can follow the links to know more about them. For now, we end by saying that the equation which took birth from heat flow has literally set the world on fire. Number 3. Navier-Stokes equation, time to fly. Rho into, partial of v with t plus v into del v equals to minus of del p plus del t plus f. Where p is pressure, t is stress and f is the body force. Seen from space, the Earth is a beautiful glowing blue and white sphere with patches of green and brown, quite unlike any other planet in the solar system or any of the 500 plus planets now known to be circling other stars, for that matter. The very word Earth instantly brings the image to mind, yet a little over 50 years ago, the almost universal image for the same word would have been a handful of dirt, earth in the gardening sense. Before the 20th century, people looked at the sky and wondered about the stars and planets, but they did so from ground level. Human flight was nothing more than a dream, the subject of myth and legends. A few pioneers began to slowly climb into the sky. The Chinese were the first. 500 BC, wooden bird, Liu Ban. 559 AD, human tied to kite, Gao. 17th century, hydrogen balloon, Europe. 1783, hot air balloon, French brothers, Joseph, Jacques. 1903, powered flight, Wright brothers. 1910, first airline, Delig. 1961, first man to orbit the Earth. And finally, in 1969, first step on Moon, Neil Armstrong, Buzz Aldrin, NASA Apollo 11. The literal ascent of humanity has changed our view of who we are and where we live, the main reason why Earth now means a blue-white globe, and if there is something around us, it's literally fluids, water and air. To set foot out of ground and into the realm of fluids, we needed to know them first. Water, as much generous, useful, and life-giving it is, studying it, is also relatively easy for it is an incompressible fluid in general. However, air is extremely different. Without proper knowledge of compressible and turbulent flow of fluid, we could have only helped in taking a man a few meters above the ground. The pioneer of fluid dynamics was the renowned mathematician, Leonhard Euler, who died in the year the French brothers invented the hot air balloon. It all began with Archimedes, 2,200 years ago. Then 1738 Bernoulli hydrodynamics. And 1757, Euler. Euler model was the first serious attempt to study the flow of fluids, now even it was still lacking. Then came this guy, Claude Louis Navier, and published his equation in 1822. 80 years later, George Gabriel Stokes started publishing on this matter. The result was what we called Navier-Stokes equation. They revolutionized the entire field of fluids and gave birth to aerodynamics. This equation is now the pillar on which aerodynamics rests. The reason we know how Pluto looks and we can go at speed faster than sound. However, solving the equation is hard, really hard. It was impossible to solve for a realistic model until humans could build supercomputers. The technique is called CFD or computational fluid dynamics. However, even with the help of computers, one question still remains unanswered: is there a mathematical guarantee that solutions of Navier-Stokes equation actually exist and is valid for all possible cases? In fact, the question is of such importance that it is one of the 7 Clay Institute Millennium Prize problems, and whoever solves it, gets $1 million. What it does and how it changed our world, the list is so big that I don't know where to begin. To end with, the U.S. Food and Drugs Administration is considering to make it mandatory that any group designing stents need to carry out mathematical modeling before performing clinical trials. By modeling they mean CFD. This is because the mathematics of blood flow is extremely intricate and intractable analytically because the walls of arteries are elastic. To add to it, the walls change shape throughout the circuit. Stents are small metal, mesh tubes that keeps these arteries open, and the exact dimension, shape, and characteristics of the mesh can only be found by solving the Navier-Stokes equation. An even more delicate case is heart bypass operation, where vein is removed from elsewhere in the body and grafted into the coronary artery. The geometry of the graft has a strong effect on the blood flow. This in turn affects clotting, which is more likely if the flow has vortices. Then only Navier-Stokes equation can say the exact geometry of the graft needed depending upon the patient's different parameters. The applications are endless and certainly begs to wonder, what equations can be even more life-changing than this? Number 2. Well, the second position is a tie again. Between Maxwell's equations. Divergence of electric field equals to ρ by epsilon naught. Divergence of magnetic field equals to 0. Curl of electric field equals to del of magnetic field by del of time. Curl of magnetic field strength equals to current density plus del of electric displacement by del of time. And Black-Scholes equation. At the start of 19th century, most people lit their houses using candles and lanterns. Gas lighting, which dates from 1790, was occasionally used in homes and business premises, mainly by inventors and entrepreneurs. Gas street lighting came into use in Paris, 1920. At that time the standard way to send messages was to write a letter and send it by horse-drawn carriage. For urgent ones, keep the horse and omit the carriage. The main alternative was mostly restricted to military and official communications, which was optical telegraph. The first extensive system of this type dates from 1792, when the French engineer Claude Chappe built 556 towers to crave 4,800-kilometer network across France. It remained operational for 60 years. Fast forward 100 years, homes and streets now had electric lighting, electric telegraphy had come and gone, and people could talk to each other by telephone. Radio communication was at the verge of being commercialized, and wireless had become the hottest word among the elites. All this can be traced back to two scientists, whose monumental insights into how universe could work in the most magnificent scale brought upon physics, the greatest revolution ever since Newton discovered gravity. They were Englishman Michael Faraday and Scotsman James Clerk Maxwell. Faraday was a son of blacksmith and was trained as a bookseller's apprentice. He lacked formal education, but that's okay, for history remembers him as one of the great experimentalists ever. His extensive experiments in electricity and magnetism led him to conclude one of the fundamental equations of electromagnetism. EMF induced equals to minus del phi by del t equals to minus del by del t of closed surface integral of B vector. EMF induced equals to closed contour integral of E vector equals to minus del by del t of closed surface integral of B vector equals to minus surface integral of del of B vector by del t. Therefore, closed contour integral of E vector equals to minus closed surface integral of del of B vector by del t. Using Stokes' theorem, surface integral of curl of E vector equals to minus closed surface integral of del of B vector by del t. Or, curl of E vector equals to minus del B vector by del t. What this tells is that over a closed surface area, if the magnetic field changes, a voltage will be introduced over that area and it will be in a direction opposite to that of the magnetic potential. For the first time in history, two completely different seeming quantities were unified. However, this was not how he described it. He described in analogies of machine and theories like he invented this concept of static field lines penetrating the fabric of space, which relays the effect of field to that subject and results in a force along its direction. He lacked the knowledge of mathematics and then was ridiculed upon. It is then that Maxwell came into action. After getting his mathematical degree from Cambridge, he went for post-graduation at Trinity College, where he read about Faraday's experiment. In 1860, he moved to King's College London, where he could sometimes meet Faraday. Finally, Maxwell embarked on his most influential quest to formulate a mathematical basis for Faraday's experiment and theories. Rest is history. They changed everything about how we perceived electricity and magnetism. And the uses? Endless. What's important though is the correction Maxwell made. Remember those static field lines Faraday talked about? They would be dynamically emanating from the source and traveling to infinity. Secondly, they would be spherical and not lines, although, eventually they changed into lines at infinity. Also, curiously, when solved for free space, Maxwell's equation gave the wave equation where V square came out to be 1 by mu naught epsilon naught, or V equals to 1 by square root of mu naught epsilon naught, or equals to 3 into 10 to the power 8, or the speed of light. Thus this proved that light is an electromagnetic wave, formed by two mutually perpendicularly varying electric and magnetic field. While this revolutionized the world of physics, there is yet another equation that affected the world in an equal scale, however, in a completely different way. The Black-Scholes equation. This equation describes how the price of financial derivative change over time based on principle that price is correct, the derivative carry no risk and no one can make profit by selling it at different price. Why is it important? Well, it makes it possible to trade a derivative before it matures by assigning an agreed rational value to it, so that it can become a virtual commodity in its own right. What does that mean for the world? Well, it leads to 1. Massive growth of the financial sector. 2. Ever more complex financial instruments. 3. Surges in economic prosperity punctuated by crashes. 4. The turbulent stock market of the 1990s. 5. the 2008-09 financial crisis. 6. And also, the ongoing economic slump. Since the turn of the century, the greatest source of growth in the financial sector has been in financial instruments known as derivatives. Derivatives are not money, nor are they investments in stocks and shares. They are investments in investments, promises about promises. Here's a simplified example. Due to rules about market stability, you have agreed to buy 200 tons of rice every year from the market. However, you see the value of rice rises every year. So, you can buy now and sell it next year at higher price. Then you become greedy and you want even more money. What you do is that you use the Black-Scholes equation to estimate the value of rice in 2 years. You then go to another guy and say that, hey look, after 2 years 200 tons of rice will be thrice as costly. I have promised the market to buy from them 200 tons rice every year, so if you pay me double the amount of what it's worth now, I will give you 200 tons of rice which I have promised to buy from the next year, which, by then, would cost thrice the money it costs now. That way I make profit now, and you make profit then. This is the mess that the equation created. What was its effect? In 1998, the international financial system traded roughly $100 trillion in derivatives. By 2007, this amount grew to $1 quadrillion. The problem was these all were a mess of virtual money. In real, the total value of all products ever manufactured for last 1,000 years, is about $100 trillion adjusted for inflation. If you can see the problem at some point, the entire system will fall like a house of cards. It happened in 2008-09 when the world lost $17 trillion, the only difference being, this was real money. Who would have imagined what a disaster an equation can cause? This equation became so important that it won Merton, who modified it later, and Scholes, Black being already dead, the 1997 Nobel Prize in Economics. We have finally reached number 1. So far, we have seen equations that changed the courses of history left and right, which makes us wonder, which equation can overpower all of them, what can be more important than all previous ones? How much more powerful and impactful can an equation get? Well, to begin with, our winner of number 1 spot for the equation that changed world is not one but rather, it's a tie, again. It's a tie between the two pillars of modern physics, the equations on which the entire universe rests. From quarks to supermassive black holes, wormholes to bending of time and light, they can make anything possible. They are Einstein's relativity and Schrödinger's quantum mechanics. Let's start with Einstein, the man synonymous to genius. His theory of relativity consists of special relativity and general relativity. Both of them consists of more than one equation. However, out of all those, comes out these two equations, which made this dude with crazy hairs, into the greatest scientist and even more, the greatest minds of all time. They are: number 1, E equals mc squared. And number 2, this. How they came and what they do, there are billion videos about that on internet, and there's a good reason for that. Equations so powerful cannot be explained in short, rather, they shouldn't be explained in short. One must know them in their full glory or don't know them at all. I will leave links to some of the best videos for you to check out if you wish to. What I will tell you though is what they meant for the world. His special theory of relativity redefined the laws of conservation of energy, mass and momentum. And his general relativity redefined the entire definition of space and time and how they interact. Together, they redefined everything we knew about world. It was the birth of a new, modern physics. When Einstein first came up with his theory of general relativity, he said that the theory is so beautiful he would feel sorry for God if it doesn't turns out to be true. Luckily for God, it did turn out to be true and made Einstein, the Einstein. Remember how I said there are millions of videos out there about his theory? Well, for few things there are none. They are The exact reason for conducting Michelson-Morley experiment in different season and different locations. How the results threaten to dispose of Maxwell's equations itself. The difference between Galilean, Newtonian and Einstein's relativity. What Minkowski's space-time distant formulae actually means. And about how he explained the orbit of Mercury which Newtonian gravity failed to do. On this, let me know, down in the comments if you want to know them, and I will publish a blog post about them then, for you hardcore science nerds. For now, we end by saying that Einstein, more than any other person in the world, deserves a universal hats off. He taught himself to think not just out of the world, but out of the universe in an age where we already thought that we knew everything. He superseded Newton's theory of gravity when even today, it works perfectly fine for 99% of cases. Only when gravity comparable to that of Sun or above comes into play, does Einstein's relativity show its true color. With no actual clue or frame to work upon, with just sheer power of his intellect, he single-handedly showed God, how men doesn't need to always learn from problems they face, how men can see through the same eyes as that of God, into the future and beyond to reveal what God has hidden under the table. While Einstein towered above all to see through galaxies, things went differently at the smaller scale. By smaller, I mean much, much smaller. Welcome to the world of quantum mechanics where nothing actually exists. All that exists is the probability of everything's existence. These probabilities interact with each other and the energy around them in ways no classical or relativistic physics can explain. It demanded a new branch of physics on its own. In 1900, the great physicist Lord Kelvin argued that the then current theory of heat and light, considered to be an almost description of nature, was obscured by two clouds. The first involves the question, how could Earth move through an elastic solid, such as luminiferous ether? The second cloud was doubt about the Maxwell-Boltzmann doctrine regarding partition of energy. He was spot on. We saw how the first question was solved by Einstein's relativity. Now we will see how the second equation pans out to be. It all began with light bulbs. When a German physicist named Max Planck was hired in 1884, to design the most efficient light bulbs possible. In short, this led him to throw away the then current theory of radiation and energy distribution, the equipartition theorem, and reinforcing thermodynamics assumptions. He proposed that energy distribution cannot be continuous, it has to be discrete. Since then, Einstein proved how light has particle nature too. By then, people had accepted that light is both a particle and wave. Then came this equation which became the central equation of quantum theory. The equation bears the name of Erwin Schrödinger. In 1927, he wrote down the differential equation. IH cross del psi del t equals h cap psi. Where h cross is h by 2 pi and h cap is Hamiltonian operator. One way to interpret this is that quantum waves are linked pairs of real waves, as if a complex ocean that actually is made up of two real waves of different heights, with the two direction of height, being at right angle to each other. Also, as time passes, the wave cycles through a whole series of shapes and each is mysterious linked to the other. It's like two waves are two faces of same wave which spin steadily around a unit circle in complex plane. The real and imaginary parts vary sinusoidally. We can solve the equation like one solves Fourier's equation, however, here we get eigenfunctions unlike the functions of space and time which we get in Fourier and classical wave equation. An eigenfunction is a multiplication of two functions, one of only space, and other of only time. Despite all the complications, it would just have been a fancy form of classical wave equation if it wasn't for a puzzling twist. You can observe classical waves, and see what shape they are, even if they are superposition of multiple Fourier modes. But in quantum mechanics, you can never observe the entire wave function. All you can observe on any given occasion is a single component eigenfunction. Roughly speaking, if you attempt to measure two of these components at the same time, the measurement process on any one disturbs the other. There are so much more, but we end here. Some are extra easy, some cannot be expressed even in thoughts. Some are small, some are big. But, they all, single-handedly, changed the course of human history.